No. I get 10 out of 10 out of 5? Means you got 10 on top. Yeah.
Good time at least.
Andrew, if you could just shift that in a little bit so that Herman can take over and have a chair. But you're speaking as well.
I am.
He needs to know how you are and you're going to talk.
Kneel before me, sir. That's okay.
Okay, welcome back everybody to the second session. Our first speaker is Gavin Pringle from the Edinburgh Parallel Computing Centre, and he'll talk to us today about current hardware for HPC, HPC and data management on Biomed. Before he starts, there's a form in front of you on the table, and we would like you to fill that out before the day is over. Thank you.
Hello, my name is Gavin Pringle, and thanks Herman. I work for EPCC, one of the partners of Biomed, and I'm going to talk about the current hardware available for high-performance computing, high-throughput computing, and data management for Biomed. There are a number of resources available, and I have 20 minutes, and obviously you don't want to hear of a list of hardware, so I thought I'd just take this opportunity to stand back a moment to try and simplify high-performance computing, so that, particularly for the non-HPC experts in the audience, so that we can all have a common terminology. So this is going to be very high-level, cartoon, Mickey Mouse description of high-performance computing. So, getting access to resources, I'll start with, so that Biomed has been granted allocations on several large HPC resources, and allocations of these resources are managed centrally through this email. So if you're keen, you can email that address. But first, high-performance computing, broadly described. A high-performance computer is a single system which has several nodes, or boxes, or mainframes, or sockets, or big lumps of iron that has a single door to it. So these nodes can be a number of 2 to tens of thousands of nodes. Within each node, you'll have a number of processing units. These are called cores. And these cores can be CPUs or GPUs. CPUs, you can have between 2 and 68 CPUs inside a single node. For instance, Intel Knight's Landing has 68 cores per node. Or with a GPU, it's a much greater number, 500 to 4,000 GPU cores within a single node. And all these cores inside a single node share the memory available to it. And then on a larger level, so you have the cores inside the nodes, and then the multiple nodes are connected together with some sort of communication cable. This is called the interconnect. Sometimes it's called the communication fabric. And there's several types of these. Some are slower, some are faster. And all of this is essentially a high-performance computer. And it does two things. It computes and it communicates. Hopefully you spend more time computing than communicating. The computation is done by the cores. And this, typically in high-performance computing, is done using computing languages such as Fortran, C, C++, and to a larger and larger extent these days, Python. So you'll notice there's no MATLAB, or R, or Excel listed in this. And then there's the communication. So the cores themselves communicate, perform the computation, but they also have to exchange information between themselves. Now this is very fast inside a node, because they all share the same memory. But it's slightly slower when you go, or significantly slower, when you go between the nodes over the interconnect. And indeed slower again when you want to write data from your local memory onto disk. And then finally, managing your job. So jobs are submitted via a job manager, and this is called a batch system. Commonly used batch systems are PBS, LSF, Slurm, Load Leveler, and to a lesser degree SGE, Sun Grade Engine. And then what is cloud HPC? This new term, essentially a very rough sketch could be that there's on your laptop or your workstation or your PC, there's a client running there, and you can submit a job that runs remotely on a distant HPC system. You kind of don't care where it is. So it will take the data from your laptop, put it onto the large machine, manage the job for you, and then take the data back once the job is finished. That essentially is cloud computing. Now, I should say this is a very simplistic view of both HPC and cloud computing, but it's just to get everybody in a room a bit more up to speed into the same level playing field. So the essentials of HPC, or high performance computing, is that typically there's a single very large application, and it uses a huge number of cores that use multiple nodes, and it requires a very fast interconnect. And then you have high throughput computing, which is typically ensembles, or what we used to call task farms. So every little job. So there's a small to medium-sized jobs. They each run on a large number, not a huge number, a large number of cores. But these jobs can run simultaneously, and you don't need a fast interconnect for such jobs. And then lastly, data management essentials. So typically, a data management platform will be running serial jobs, but will be associated with a very large shared memory resource, what some people call a fat node. So that'd be a large number of cores, but a huge shared memory space. And data management platforms will also have a very fast interconnect to disk, much faster than other HPC or HTC platforms. So, what do we have available to us at Comp Biomed for these three types of systems? So for HPC, we have tier 0 platforms. I should perhaps describe the terminology here. We have tier 0, tier 1, tier 2, tier 3, tier 4. These describe a kind of pyramid of computing resources. Tier 0 is the very top. It's typically a very large supercomputer that a single country can't afford. Then tier 1 would be a very large supercomputing system that a single country can afford. So that would be like ARCA in the UK, for instance. And then tier 2 would be something perhaps more bound to a university. So for HPC, we have two machines in tier 0 currently available. That's Mare Nostrum in Barcelona and Marconi in Cinica. I've put Zi Supermuc in grey there. It's not currently available across Comp Biomed in general, but Peter's working on an application to get the allocation. Tier 1 platforms, we have EPCC's, or the UK's ARCA service, and Cartesius in Surf Sara. And then the tier 2 service, is really more tuned to high throughput computing. So the interconnects might not be so fast, but you have direct. So the two systems we have for high throughput computing are CIDIS at EPCC and LISA at Surf Sara. And then lastly, for Comp Biomed, for data management, we have ARCH's, or the UK's research data facility, I should say, which is attached to ARCA. And this is the RDF and the DAC. So I'll run through these one by one. So on a very, very general basis, so we don't get overloaded technical detail. So this is Mare Nostrum. It's one of the nicest supercomputers in the world, we think. It resides inside a church. It used to be, after it was a church, it was a theatre, and they have these velveteen red seats up on the wall, and they use that to bring in the politicians, and they sit in the red chair, and then they have a light show. It's all very impressive. And the computer itself is in a glass box. You can't see it in that photograph, but the cooling is also, underneath the machine, is also in the glass box. So it's very nice to look at. Anyway, so there's 48,496 cores in total. These are Intel Sandy Bridge cores. And there are 16 cores per node. And the interconnect is InfiniBand. And the cycles available to comp Biomed is 150,000 core hours. Now there's lots of information missing from this slide that I think isn't necessary for a very general understanding of what HPC is. We don't have the memory per node, because that varies. It's a heterogeneous cluster, so some nodes are bigger than others. It also has Intel Xeon Phi processors, sometimes called Knight's Landing. But we don't have that as part of our allocation to comp Biomed, so I haven't listed it here. The next, these are alphabetical, by the way, just so I don't offend anybody. But these are all in, so these are the tier 0 resources. And the next one is Chinook, the Marconi. This is through Prace, and this is calls 12 and 13 lumped together. And we have, it's actually two machines. One is a 27.875,000 Intel Broadwell cluster. And then they have the Knight's Landing cluster, which is a smaller number of cores. And they have 36 cores per node for the Broadwell and 68 cores per node for the Knight's Landing. In some sense, Knight's Landing is halfway between a GPU and a regular Intel Broadwell, for instance. There's a lot of cores sitting on there, but if your computation is memory bound, so you don't have enough sums to do, you're trying to pull the data onto you can't pull the data onto the node fast enough, then the performance isn't so great. So Knight's Landing is you have to for a particular simulation it might work very well on Knight's Landing, but it might be very poor on GPUs. Or another simulation might work well on GPUs, but not so well on regular high-performance computing. Anyway, that was a sidestep. So the interconnect that Marconi uses is Intel OmniPath, which is actually different from every other HPC system we have access to. They're all InfiniBand or Aries. And the cycles available to the Centre of Excellence in general is over 81,000 CPU hours, but that's only until the end of August this year. This is a Prace, available through Prace, and it's the only external resource, i.e. not from a partner or an associate partner, to comp Biomed. Then we have Zi Supermuc. Again, I put this in grey because this isn't currently available, and my talk is about what's currently available. Total number of cores are over 241,000, and they have a mixture of Intel Xeon Sandy Bridges, Westmere, and Haswell Xeons. The number of cores per node varies. The interconnect is InfiniBand. Hopefully this will come online soon. And then we drop down to tier 1, and this is ARCA at EPCC up in Edinburgh. It's a cluster of Xeons and Xeon Phis. Knight's Landing, Xeon Phi, it's the same thing. And we have 64 cores per node, and the interconnect is Aries. This is a Cray proprietary interconnect, and it's extremely fast compared to the speed of the chips. And the cycles available there are 1.9 million CPU hours on the Xeon and 28,500 CPU hours on the Xeon Phi. And then Cartesius at Surf Sarah, that's the other tier 1 platform we have access to. This is a very heterogeneous machine. It has Knight's Landing units, it has GPU, it has regular multi-core processors. So the number of cores we have on the machine available to comp Biomed is, that can't be right. There's a number missing, so it's almost 41,000 cores or of the Intel Broadwell, and 132 nodes, that can be right either, of GPU, sorry. And the number of cores per node varies depending on whether it's GPU or the Broadwell. Again, it's InfiniBand. And the cycles available to comp Biomed in general are 1 million CPU hours. Then dropping down to the high throughput computing. So this is a tier 2 machine, much smaller. This is 2,000, just over 2,000 CPU cores. So we're going much smaller, but it's much more, shall we say, accessible. It's not when you submit your job into the queue, you'll run very, very quickly. It's more, this machine is more business orientated. So we don't look for 96% utilization, because that just means that you're going to have days waiting in a queue. So we'd rather see 50% utilization, which means anybody can, when they log on, they can their jobs will run. So it's more of an urgent computing environment. So we have 36 cores per node. We have InfiniBand again. And on this machine, we have 40,000 CPU hours. I should say that all the cycles I state are per annum. So next year, we'll have another 400,000 core hours. And that's for all the platforms. And then the other tier 2 system we have access to is Lisa, also in Amsterdam at Surf Sarah. It's slightly larger than Cirrus, over 7,000 Xeon cores, and they have 2 types of nodes. They're connected with InfiniBand, and there again the annual allocation is 700,000 CPU hours. 5 minutes. Okay, thank you. So lastly, the data management. Our intention are for people to do their pre and post processing work, which is typically done with serial codes that needs a lot of memory. And so this hangs off Archer very closely, but it's a UK facility, so everybody can use it. So the RDF is the storage unit, and the DAC is the computational element. The DAC is the data analytic cluster, and that's 304 cores, a mixture of Ivy Bridge and Westmere Intel processors. And we have either 20 or 32 cores per node, connected with InfiniBand again, and it's currently free. If you are an Archer user, you get free processing power for your pre and post processing requirements, if you like. And this data facility has a very fast connection to the RDF, or the Research Data Facility, or I should say the UK Research Data Facility. It has 23 petabytes of usable storage with a further 48 petabytes of backup. And all nodes are high bandwidth, direct InfiniBand connections to the RDF disks. That should be all the DAC nodes have access to the RDF disks. But again, if you're running on Archer, then you can use the DAC for pre and post processing. And again, it's currently free. So just a couple of notes on all of these platforms. All of the cycles stated are per annum, except for Marconi, which I've already said. For all of them, industrial partners need special permission to access it, and none of them can be used for commercial purposes. This is except for EPCC Cirrus, because it is actually an industrial-facing, cloud-based HPC system. So we want people to use it for commercial purposes. And indeed, it's quite underused at the moment, so when you submit a job, it'll run quickly, but there's an idea of urgent computing, where maybe you need your results tomorrow, or more urgent, you need your results in an hour, or yet more urgent than that. And so we're looking at the American system of introducing tokens, where a weak token will put you to the top of the queue, and a stronger token will swap all the running jobs to disk, and your job will run immediately. So we're looking into introducing that as a feature. So 2 more slides. So how to access your HP service of choice. I mentioned this already. That's the email address, centrally managed by UCL. And when you apply, you have to state which machine you'd like to use, the size of the allocation that you would want. Don't grab all of it, it's to be shared. A brief description of the problem to be investigated, and the list of the codes that you wish to be employed. I should add that a lot of these HPC services aren't just cycles, they're also people. So you might want to have your code parallelized or tuned for a particular platform, or better still, tuned to be portable and parallel. So all the academic departments offer that service as part of your allocation. And the URL there is for just an exhaustive list of what is currently available. And that's it. Do you have any questions?
Are there any questions?
Oh, yes, hello.
Thanks very much. I appreciate you focusing on the CP piece, the groups, computers. Sure. But earlier on, one of the speakers showed a list of the most powerful computers that are around.
Yes.
Are there any plans to access, as more of these HPCs come on stream, to add to the available resource within the group?
So I can't answer that question, but I would like to say one thing first. The list of the most powerful machines in the world, that's based on running LinPack, which is a numerical analysis package. But simulations don't all run LinPack. They do very strange things. They use the communication work. They do a lot of disk. So that ranking of powerful machines is very much kind of a press politicians ranking. So just because a machine's high up on the list doesn't necessarily mean it's a fast machine for your simulation. And a lot of the machines I've referenced are in fact on that list. So Marconi and Mare Nostrum and ARCA, they're all on that top 100 list. But are there plans afoot to get more of these platforms on? Peter?
So the answer to that is, this is an outward-facing centre of excellence. You've shown the core partners. I show an expanding list of associate partners. The next speaker is from Hartree Centre. Hartree has capabilities they'll be telling us about. Technically, LRZ's an associate partner. This list won't end. There are growing numbers of cloud resource providers coming into the project. The beauty of this is we have a community and we pull down resources as a community and farm them out among ourselves. As someone was asking me at the coffee break, one of the problems with HPC is it seems to be the preserver of an elite group, and you have to pass barriers, like submitting grant proposals. That does inhibit some users. This community can manage allocations as you just described and encourage people to move up the stack by support as you described, in order to do bigger, better, faster and different things than they currently can. But if you try to make a proposal flat out with no track record into one of the regular bids, you won't get anything. So this is a mechanism for trying to bring people on board and then, in certain circumstances, pitch for very large allocations where they're necessary, and we can show we have the expertise to do so. So that's facilitated by the consortium, and the associate partners get access to these allocations as well as the core partners at this point. So that's another reason, if you're interested in this, or becoming an associate partner in the project. Some can contribute resources, others will take them out. And right. One other thing I could just add in there, because you mentioned the support function, which is very important from the people trying to port codes onto these platforms and to do things like benchmarking that I reported. And one very interesting thing with you right now is to use some MIST environment to be able to plug in a code, which is called Romance, yes, with the latest time-stepping algorithms that we have access to that will enable us to take not 2 femtoseconds, but 4 and maybe 8. And that's a dramatic potential increase in the turnaround speed. So it's not just the hardware, but it's algorithms that make a big difference.
And we have a work package within CompBiomed to look at these algorithms, to port codes to platforms on behalf of the end users.
Okay, I suggest we take additional questions during the breaks and let's move on. So thanks, Gavin, again. Next speaker is Neil Morgan from the Hartree Centre. Neil. Neil will talk today about accelerating the adoption of data-centric and cognitive technologies.
Good afternoon, everyone. Just to introduce myself, my name is Neil Morgan and I'm part of the Hartree Centre, responsible for the Future Technologies programme at Hartree. I'm actually standing in for Robin Pinning, the CTO today, and I'm just going to be talking about a little bit of background about the Hartree Centre and what we do, and also about how we're looking to accelerate the adoption of data-centric and cognitive technologies. So, the Hartree Centre comes out of the 2011 Dominic Tilsley report, which identified that there were significant economic advantages in terms of driving the adoption of software and simulation within industry. That led to the funding of the Hartree Centre in 2012, initially with a significant partnership with IBM as they focused around industrial engagement. That was followed up in 2014 by some additional funding to the tune of about £19 million, and this allowed us to broaden the remit of the centre to start to look at big data and energy efficient computing, an area that I've been previously involved in. But that's all been leading up to the 2015 investment, which was for £115 million, so quite a significant amount of investment from the UK government. And this is around a 5-year programme of R&D, again in collaboration with IBM, but very much focused around data-centric and cognitive computing, and how we can, again, drive the benefits of those technologies and evolving expertise into industry for economic benefit for the UK. And that's included embedding an IBM research group, so we have a significant number of IBM researchers who are now working alongside staff from the Hartree Centre, the Science and Technology Facilities Council, based at Daresbury. And what we're looking to do is extend our industrial and scientific reach and ultimately produce a set of digital assets. And digital assets can mean a number of things. It can be software in terms of tools, applications, middleware, but ultimately we're looking to do things like lower the barrier to adoption for HPC, big data analytics, machine learning and cognitive computing. So it's quite a broad portfolio. So the mission of the Hartree Centre is to transform UK competitiveness through the application of those technologies that I've just talked about. And we see real advantage and opportunity in leveraging the capabilities of hybrid cloud, whether it's on-premise or off-premise, to provide readily available and accessible services to industry. So we're looking to work closely with a range of partners, technology partners, academic partners, to undertake R&D, to develop prototypes, do proof of technology and proof of concept work that will ultimately lead to better products and services that are delivered faster and cheaper for our clients. So what's our focus? Well, our focus is around 3 main areas. For phases 1 and 2, it's very much around consultancy, so working in traditional areas of HPC and big data analytics. As I've said, we've expanded that to energy efficiency as well, and starting to look at machine learning and cognitive computing. Very much the thrust for the work we're doing at the moment is around platform as a service. So again, this is where the cloud piece comes in. How can we develop the tools, the platforms, all of the capabilities that will enable users across the piece, both from industry and from academia, to leverage the capabilities available through cloud and address some of the opportunities and challenges that are there. And also undertake R&D, proof of technology. As I say, we're really looking to build this portfolio of digital assets and capability that will help to improve the UK economy. So, in terms of the focus of our R&D within the Hartree Centre, one of the things we've identified is a convergence of a number of different areas. So we see HPC, machine learning and artificial intelligence and big data analytics all coming together as part of much more complicated workflows. One of the challenges is how do we simplify those workflows and automate those workflows, and I'm going to talk a bit more about that as I work through the presentation. So there are 3 key themes that we've identified: convergence of data and compute, complex workflows and applications and architecture, and I'm going to go on to talk about those in a little bit more detail. So, the convergence piece is very much around combining big data frameworks with HPC, so Spark is a good example, Hadoop, MapReduce, these sorts of frameworks which do facilitate ready data processing. How can we integrate those into the cloud and make those readily available and accessible so that you don't have to be an expert? Much of HPC and data analytics historically has been focused around, as I say, complex workflows where you're writing scripts, you need to understand the command line interface, etc. It's not really, it's an expert domain. We need to try and move away from that, give people the capabilities to use this technology to solve industrial problems. How do we deal with the issue of data? As some of the challenges we face grow, I mean, Peter's talked about this today, the size of the data sets that we have as well. How do we manage those? How do we process those? How do we do that efficiently, both in terms of computationally efficiently and energy efficiently? So we're looking at accelerated architectures. Gavin, the previous speaker, was talking about GPUs and Knight's Landing, but there's also hardware such as FPGAs, which we can use to reduce latency, increase throughput. The challenge there, of course, is how do we program those devices? It's not necessarily straightforward. So in terms of taking code and making them run on some of these new exciting architectures, there are big challenges there, and Hartree is looking to try and solve some of those in collaboration with our other partners. And sensitivity to the data as well, again, is a key one for our industrial clients, whether it's in the health sector or engineering, wherever it might be, whether it's Rolls-Royce or Unilever. Making sure that they can run their applications and their data is secure is extremely important. So workflow orchestration, this is one of the big areas of focus for Hartree as well. So we're really keen to develop new ways of enabling our users to more readily submit their jobs and applications. As I say, in the past it's been very complicated. You needed to be able to use Linux, use command line interfaces, pre-process data, scripting, etc. We need to start to build and design GUIs to make access to these capabilities and services much more straightforward, and as I say, lower the barrier to adoption. We want to automate as many of these processes as we can. Start to use machine learning to optimize as well, and ultimately, as I say, lower the barriers to use and adoption. And data locality and energy awareness has already been talked about in some of the other talks, but the whole automation piece is related here as well. So at Hartree we've done quite a bit of work around energy aware scheduling, how we can identify the most appropriate place to run a particular job, in terms of the overall energy, but also the runtime. So how do we do that and do that intelligently and make sure that the job runs in the most appropriate location? It's a really exciting time within HPC. We've already heard today about different architectures. There's an increasing array of architectures, but one of the challenges we have is how do we refactor and optimize some of the pre-existing scientific codes that are out there. Portability, extensibility, research software engineering, all things that you'll hear about, all very important for Hartree. Within the centre we have some work that's going on at the moment around research software engineering. We're looking to embed those principles within what we do within the centre. We're talking to EPSRC, who I know has funded some fellowships around research software engineering, so that's a key strand of what we're doing. Benchmarking and evaluation of these architectures is obviously key as well. We need to understand the capabilities of the hardware, we need to understand the requirements of the software and the applications. How do we best marry up the applications to the hardware? So again, we can run those applications in the most appropriate place, whether that's for overall performance, for energy, or whatever the client requirement might actually be. So there's a whole coordinated activity around benchmarking and evaluation. We have quite a long time scale around this. So whether it's Knight's Landing, which is just recently on the market, or looking into the future at other technologies, whether it's optical compute, whatever it might be. And collaboration and engaging with partners and other vendors is absolutely key. So I've already mentioned IBM. We're obviously doing quite a lot of work with Atos as well. We just purchased a new machine. a new production machine, which is I'll go on to talk about a bit more in the future. Hartree is very keen to try and influence the future of architectural design so that we can bring our benchmarking activities and our industrial engagement to bear and ultimately improve the EU bargaining position for future resources. Okay, thank you. So, in terms of our R&D output then, as I say, we're looking to produce a range of digital assets. These are the outputs which will effectively form products that we can then deliver to run across a range of these emerging architectures to try and automate and simplify workflows, and ultimately looking to deploy services, HPC and deep learning as services in the cloud. So just in terms of some of our machines then, Hartree is quite unique in some ways because we have quite a broad range of architectures. The latest addition to the machines that we have at Hartree is the Scarfell pipe machine. This is a Soprano architecture machine. I'll let Andy talk about that in a bit more detail. It's probably part of his talk. But it includes Intel Xeon processors and night landing, a total of 3.4 petaflops. We're also going to host the Oxford Jade system at the Hartree Centre. This is a Bull DGX1. We have 2 Power 8 systems as part of the IBM collaboration. The latest machine is a Paragon machine which includes the NVIDIA P100 GPUs. We do some work with ARM as well, and through Lenovo and Cavium. We have what we think is probably, well currently anyway, the largest ARM 64-based supercomputer in the country, which is actually close to 2,500 cores, and a range of other more standard architectures as well. Okay, thank you for listening.
Any questions?
Just going back to the question that was asked to Gavin about capabilities and resources, from the perspective of Biomed, the tie-up which Andy will talk about with the Bull machine, Bull being a full partner, and you're an associate partner, gives us real opportunities here because Bull has certain commitments into the project for users.
Sure.
And then I also understand, though I don't think you mentioned it, that there's quite a push for Hartree to support SME, maybe UK-based SMEs which have preferential access. Are you going to say something about that?
I will.
Because
The
there are
answer to the
SMEs
question
in this
is yes.
project and how we work.
Access to resources, absolutely.
Do you have any other comments on that? SMEs are prioritised for access to that resource? Or?
I don't know, to be honest. In truth, Peter, Robin would probably know more. Maybe Andy.
No, not specifically. In fact, the industrial usage actually, bigger organisations are better because they're going to make better commitments, broader commitments on the whole. But it's a mix.
Okay.
Yeah, and I'll touch on that.
Let's thank Neil again for a nice presentation. And our next presenter is Andy Grant from Google Atos, talking about HPC and deep learning as a service.
So this will very much follow on from Neil's talk and cover some of the same points. So I'm Andy Grant, head up the HPC and Big Data team for Bull in the UK, and as Peter mentioned, we're a full partner in Biomed. So I'm going to cover a brief introduction to who we are, because not everybody knows Atos, talk about HPC and deep learning as a service, and specifically how we're going to do that, how we do it already, but also the work we will do with Hartree. And I've adjusted my talk a little bit this morning to cover big data workflows as well, because that's been touched on a number of times. And then, if we get to it, we'll talk about what we're doing around security as well. So Atos is a roughly $12 billion company, global organisation, 100,000 employees, but European-based. Very much our DNA is European. Atos acquired Bull 2 years ago to head up its HPC function. And so it's the largest European IT services organisation and the largest IT manufacturer in Europe. And in the HPC space, we have a range of kind of offers and services that I won't dig into, but just to say there's a broad portfolio from systems through consulting, etc. So high performance computing as a service, there's been a very interesting discussion this morning, and a lot of the points that I raise on this slide I think have been drawn out through some of those discussions. Why is it an attractive option? Well, the little bar chart at the top there is perhaps an exaggeration of a typical environment where a site will have a certain capacity, and at some times of the day, sometimes of the month or whatever, you need more resources than you have available, and therefore you've got an unmet need. At other times, you've got more resources than you need, perhaps over the weekend, so you've got wasted resources. So the whole HPC as a service, if you like, paradigm is to try and move away from that. The other aspect is total cost of ownership, and particularly when governments keep changing the rules on how funding for CapEx and OpEx is handled, the two things are never aligned. You end up with a complete mess. You can never get the people to support the systems at the same time as you can buy the machines, etc. And you've always got depreciating assets. And we talked on data center energy efficiency. HPC systems, particularly larger ones, can take hundreds of thousands of pounds to power and cool. And then aspects of how do you manage distributed teams, distributed projects, etc. So HPC as a service intends to address those issues. And benefits, increased agility, generally increased runtime, increased return on investment, and increased security. I think the fear a few years ago was cloud. How can I trust? How do I know where my data is? How can I trust that it won't be hacked, etc. And as I mentioned this morning, some very large international, very high-profile projects, such as the Olympics, are now running entirely in the cloud. But all of these arguments could be used as general arguments for why cloud is a good idea. On the other hand, my view is general purpose clouds generally do not work for HPC workflows. Why? Well, at scale, typically, HPC is around performance, around trying to get the most out of the system, so you need to be close to the metal in the sense of you don't want layers of software getting in the way. Large-scale HPC systems such as ARCA or our own systems, the team spend an awful lot of time optimizing the operating system, so you don't get a daemon popping up now and then which just screws all your results. HPC applications often need to bypass the OS kernel to be able to scale. Certainly to scale to hundreds of thousands of cores, this is a critical thing. Often HPC, you need tuned hardware, so that might be accelerators, or it may just be you need access to large shared memory, which typically you're not going to find in a general purpose cloud environment. Parallel file systems, critical for performance, as we've heard a number of times. And batch scheduling, again we've heard a number of times, to manage workflows. So these are all reasons why general purpose clouds, and I take the point that not all clouds are the same, and there are HPC elements of some general purpose clouds, but a lowest common denominator approach to cloud adoption generally will not work for HPC, in my view. So how can you get the benefits of a cloud for HPC without some of those drawbacks? Dedicated HPC as a service offerings. So our solution is a thing called Extreme Factory. The idea behind Extreme Factory is to make access to HPC systems easier for non-expert users, but also not restrict it to non-expert users. Expert users certainly access the systems as well. And do that via easy-to-use portals. In this case, it's a thing called Extreme Computing Studio, XCS. And also to enable remote visualization, critical part of the HPC process, to be able to visualize your results. And key point here is keeping the visualization aspects close to the point at which the data is generated, so you're not moving vast quantities of data. So we have machines dedicated to Extreme Factory, but let me just explain essentially how it works. A user will go to the portal, they could use their own local facility, which we call Extreme Factory Private, or they could go to either one of our computing centres or a private centre somewhere that's offering Extreme Factory as a private cloud service, or a pay-as-you-go public cloud service. And the portal, this is the key bit, because this is where authentication, job management, license management for the applications, etc., all happens. So this is the crucial bit where you interact with the service. And there's a combination here of bespoke software development, which is typically open source, but also third-party applications. Somebody mentioned ANSYS this morning, for example. So how do you integrate those third-party applications? The picture here shows what a session might look like. So the front window here is what the portal would look like. You access that and you click on one of the buttons, which would bring up the list of applications. So the window on the left is showing for this particular user what applications they have available to them. So they clicked on an application and it will bring up a job submission form. That job submission form you could expose or you can hide as many parameters as you want. So if you want the ability for non-expert users to be able to run an AMD job, upload data file, how many processes do I need, press go. If you want a more expert user, then you would have more parameters exposed. And you can do this based on user class. So if me as a non-expert were to log on to this, then I'd want the minimum perhaps. Once the job's submitted, you can then monitor what's going on the system. And we've got a vast quantity of applications that are already portalized, if that's such a word, that are available within the portal. And these range from many ISV codes such as ANSYS, LS9, etc., of the automotive industry perhaps, to molecular modeling codes, life sciences codes. And typically it would take half a day to create a portal sheet for submitting another application. Into that. And then we get on to visualization. So your job is now running on the remote facility, you've uploaded your data file, away you go. You want to see the results. The one thing you absolutely don't want to do is generate a big data file on the remote system and then have to pull the whole lot back to visualize it locally, because the cost of transferring data will be too high generally. So it's important that the visualization is co-located with the HPC resource, which is co-located with your data. So run the visualization, attach it to the job, and then all you're sending back to your local system is a stream of pixels. So you're sending mouse movements and control and rotation commands, etc., to the system, coming back as a stream of pixels, which is very secure. Like nobody's getting access to your data. The maximum they could see is a snapshot of a stream of pixels. And by the way, you're sending it back over an encrypted tunnel, so actually it'd be very hard for them even to do that. Your intellectual property is therefore protected. Now, we have, maybe the next slide. So, one of the things we offer is the ability to tailor this portal. So there are a large number of companies who will take what we've got and tailor it for their own private cloud. So here's one example of a company, EXA, who do CFD modeling, who do exactly that on their own private cloud. So you could imagine Biomed having its own private cloud in this case. And we have a large number of customers doing it in different ways. Perhaps one of the biggest known ones is Renault. So Renault do all their crash simulation and all their finite element work using this mode. BMW, I mentioned earlier, are a new addition to this list, doing similar kind of work. So what are we doing with Hartree? Well, my view is that it's important that we make available the resources that have been publicly funded particularly for industrial engagement, available to the broader community and to projects such as Biomed. So Hartree, through a recent procurement, have just bought a large supercomputer from us called Sequana. The details of it here, so 3.4 petaflops. It has a large number of regular x86 Xeon nodes. It has a very large number of Knights Landing nodes. It has large memory nodes, etc. So you can imagine a scenario where you submit your jobs via Extreme Factory to a specific queue. So you've got you're doing some pre-processing where you need large shared memory, for example. So you submit to a queue which targets those high memory nodes. Or you want just the maximum compute you can get, the maximum number of cores, so you submit to the Knights Landing queue, for example. So we will be putting the Extreme Factory software on this Starfelt Pike system and offering that as a service both to the academic community and to industrial collaborators, partners, etc., as part of the overall industrial engagement. And some of that will be resource that's freely provided, and some of it will be paid for, because the system ultimately has to become self-sustaining. And Neil mentioned deep learning, the JADE system. So this is a collaboration between ourselves, Oxford, and Hartree to host a national deep learning service based on NVIDIA GPUs. So in this case, it's 168 Pascal GPUs. So I'm not sure how that translates into GPU cores, but a very large number. And a key thing here is these GPUs are 8 GPUs per block of memory. So they're fat GPU nodes. And the first family of GPUs to be connected via NVLink, which is the NVIDIA high-performance interconnect between the GPUs. So that system is currently being installed at the moment. It should be going live very soon and offered out as a service. And the intention is, in the fullness of time, that will also sit behind the Extreme Factory portal as well. So you would have a queue that you submit to the GPU nodes. And for those of you who aren't familiar with deep learning, and I'm thinking Anna here, the problem you described earlier. So deep learning is an artificial intelligence technique using deep neural networks, where you have a system that is trained over time. The example I use quite a lot is mammography scans. So it's a very mundane human task to scroll through lots of images trying to spot something that's a very small feature in a very fuzzy image. If you can teach a system to do that and get the accuracy higher than a human, then it becomes a much more productive task and a much better use of the human resource. So you could train the system with thousands of mammography scans to spot where a tumour exists. Once you've done that training set, which is a real HPC problem, then the next stage could be, okay, take my latest patient, scan them against the reference data set. Do I have a match? If so, look for further analysis. So it's those kinds of problems that we're looking for with the deep learning system, and ultimately with the intention that this will become part of regular medical care. Okay. So that's the HPC deep learning as a service. The other bit I just wanted to mention, because it's come up a number of times this morning, is around workflows and big data workflows. Now, anybody who is in the big data space knows it's the thing of the moment, and every week some new technology pops up. This was a snapshot from last year of the big data technologies. So how, as a researcher, are you to make anything of this? So what we try to do is filter out what we believe to be best of breed components within each of those different areas. Our data scientists will work with the different organizations to say, okay, well, we know there's a class of batch issues. We know there's a class of analytics, etc. So we'll take those best components and we put them into a service catalogue. So a service catalogue that then becomes available to a researcher or an end user or a developer to create a big data application. So if you've got an application where you know you need to ingest data from a streaming system or from an MRI scanner, you need to do some analytics on it, you need to do combine it with some other data, and then you need to visualize it, then you can plug together the appropriate components from the service catalog to create your big data application. And this is all open source, by the way. And then up here, somewhere, there'll be a button that says deploy. And then you can deploy that on Azure, on Amazon, on our cloud, or on premise. Now, the neat thing here is not all of these components need to run on the same machine. So if you imagine that you want to combine genomic data that's coming from sequencing machines with the phenotype data that's contained within a patient's electronic health record, combine that to look for any contraindications to their treatment. So you might have, as part of this, a genome sequencing pipeline that's running optimized on a GPU cluster. Goes off, runs there, the data is brought back into the framework, and it's combined, and then hopefully you get some improved diagnosis over time. So that's one of the things we're working on, is how we can embed some of those different components into the framework. Okay. So let's just go through that. One of the other aspects of our involvement in the project is around application optimization and some of the higher value services. So as well as the cloud layer that I mentioned there, our team have involvement in terms of application optimization. So can you optimize for I/O? Can you put your application to GPU, etc., etc. So there are allocations of time from our Centre of Excellence in Parallel Programming to help with that activity. And on the right-hand side there, all within a framework of security. And so CPP have resources dedicated in the project to help you do this. And if it's a case of how do I take my 1,000 node application and get it going to 10,000 nodes, or how do I reduce my runtime from 6 hours to 2 hours, hopefully we can help with those problems. Because we have people with expertise in each of these different domains. So I'm probably at the end of my time, so I won't talk about security. But if you are interested in any of these aspects, please feel free to get in touch and I'll explain more happily. And apologies if I've talked very quickly there. I had more to get through than I should have, than the time allocated. Apologies.
Any questions?
Yeah, on the third-party license,
How does that work?
do you have to pay extra? Because we have our own StarCCM plus power license. If we use that.
Yes, that's exactly it. So bring your own license model. Yeah. So one of the parameters that would be exposed is paste your license key, and that you could paste that into there.
I have a question about deep learning. In many cases, the data is private and needs to be encrypted. Do you have solutions for computation and encrypted data, like homomorphic encryption?
We are working on homomorphic encryption. Yeah. In terms of, there are a number of partners we work with in the secure government space who are addressing that problem. In the health space, where I was talking with a company yesterday, in fact, who were looking at how we can address this problem. They tell me they've got a method where they can separate the patient identifiable data from the bulk of the data in a way that allows the analysis to happen, the deep learning training to happen in a way that doesn't lead back to identification. So I don't know the details, but it's an active area.
I have a question about the deep learning. Clinically, training, you need a lot of training data, and with respect to the clinical data analysis part. So how to deal with it and the application that we have to make.
There are, in some cases with clinical data, there are data sets that have already gone through the training, if you like. So the mammography one I mentioned, that's a case where, you know, I guess yeah.
The complexity is very high, so you need a lot of amount of segmented data in order to use it for.
Yeah, and it's a challenge. It's a much a logistical challenge, say within the NHS. We work. I don't know where UCLH is, but that way I guess. So we're working with UCLH to try and look at how we can deploy these technologies in a healthcare environment. Because it's, you know, it's MRI data, it's electronic health record data, but there's a general recognition that within that body of data, there's a massive, very valuable information if we could sort out as much the political access problems as the technical ones.
Okay, let's thank Andy again. And it's lunchtime now. Please try and be back here 1:45, and we can start again on time.
I think this sort of time came about before, movements came about before, and I think that kind of changes things. It should make it a whole lot more accessible. I would love to. Well, I'd love to do Michael Reeves. I'd rather see people I would love to do.